Okay, so this is the midterm review session for EGME 541, fall 2020 semester, for for the first midterm. Okay, so I looked at the online poll on Canvas, and it looks like the most requested topics to go over are frame equations, direct stiffness, and there's even one vote for beam equations. So I at least want to get through the first two today. They're all kind of branches off the same tree. So by reviewing just a few of these, we're basically gonna be reviewing all, because everything in this first unit is kind of really based off this this idea of the direct stiffness method. And so I know frame equations was requested first, but I think the best thing would be to start with the direct stiffness method, what that is, and then from there, because from direct stiffness basically everything branches off from there. Okay, so let's start with the direct stiffness method, right? And so the whole idea with the direct stiffness method is that it's one way to implement what what many people know as the finite element method. Okay. And so if you kind of place, the direct stiffness, in terms of its importance in the finite element, pantheon, I guess you can say, that direct stiffness is usually kind of the first stop for a lot of people learning finite elements for the first time, mostly because it's fairly intuitive and it kind of builds almost directly off, what you guys or what especially mechanical engineering students understand about like structural equilibrium and designing structures and trusses and beams and frame elements. So and so it's a nice way to kind of introduce just the idea of finite elements into like an area that's relatively familiar with at least a lot of mechanical engineers and civil engineers, which are kind of the two main fields that use finite elements. Okay. And so the idea with direct stiffness, I know we introduced it with the concept of springs, but direct stiffness is kind of just a way to kind of approach the problem. Okay, and so the way that we do these kinds of problems, as well as all the trusses, the beams, and the frames, we all follow the same framework. Okay, and so the first thing that we do, even actually before that we start writing down matrices, that the first thing that we do is we examine the problem, we analyze the structure, and we write down or we note what all the geometrical and material properties are for our structure. So this is always the kind of the first thing that you do, and a lot of times we do this kind of implicitly, because you're presented with a problem, you're presented with a certain structure, and then you're going to just naturally see what are the lengths of all the elements, how much are they rotated, what's the Young's modulus, what's the moment of inertia, what's the cross-sectional area. So that's kind of the first thing that we have to do, is just note first of all, how many elements do we have, how many material properties, and all that stuff. And kind of along with this, we have to, another good thing to do is to note what all the boundary conditions are. Okay. Because those boundary conditions are going to have a really big impact on our results. Okay? And then later on, we need to manually input these into our global stiffness system. Okay, so I'd say that's the first thing. So just basically just noting, just take apart the structure, make sure you get every single detail and write them down properly. Okay, and so from here on, this is kind of the familiar process that, hopefully that you guys all should be experts at now. And so the next step is we need to write down the element stiffness matrix for every single element. And so for each structural element that we have in our model, we need to write down what its element stiffness matrix is going to be. Okay? And of course, which element stiffness matrix that we use depends on what type of element it is. Okay. And so if you're doing a truss problem, if you're doing a beam problem or a frame problem, all of these have their unique element stiffness matrices. And even, for trusses, and at least for trusses and frames, we did a lot of practice problems where we did them in 2 dimensions too. And so we had to do the transformation between the local coordinate system and the stationary one. So make sure you know how to do that and how to account for that in the element stiffness matrices. Okay? And I'll note right here too that for most of the problems that we did in the class so far, most of the structure has been comprised of just one type of element. But definitely be on the lookout for problems where I'm going to mix some of the elements together. So we saw a little bit of this where we did a problem with a truss or a beam with a spring, or like maybe a beam with a frame. So really pay close attention to what type of each of the elements are in the system, and make sure you apply the correct element stiffness matrix for that for you. Okay, so the second step is, computing these element stiffness matrices. So all this basically is just kind of plugging and chugging into the matrix formulas that we had in the class. All right, so the next step is, once we have all the element stiffness matrices, we need to assemble them into the global system. Okay. And so remember, the global system represents a system of linear equations that we're going to solve for all the nodal degrees of freedom in our system. Okay. So this is kind of I mentioned it before, but the goal for a lot of these computational methods, we're doing finite elements in this class, but there's also things like finite difference and finite volume, is that you want to discretize, you want to formulate your problem in the form of a system of linear equations, because solving a system of linear equations has been studied, for eternity, and computers are actually really, really good at it. So for now, basically what you're seeing is that, we're taking a structural problem and we're turning it into a system of linear equations. And then after the midterm, what we'll see is that, we're going to use, a method called the Fullerton method to transform a differential equation. It can be ordinary differential equation or a partial differential equation into a system of linear equations. Okay? And this transformation between, something that's really complex to, a system of equations is, that's kind of something that's shared with a lot of these computational methods. And so for the direct stiffness method, the way that we get this linear system of equations is that we take all the element stiffness matrices and then we form them, into one kind of bigger system. Okay. And remember, the most important thing for the assembly is to kind of keep track for each element stiffness matrix, what nodes do they act on? Because what nodes do the elements are connected to, this tells us where in the global system that we need to put their entries. And so that part's really important because, you know, you want to stack, you know, because there's always going to be some overlap in a global system. You want to make sure you're overlapping on the right places, and you're putting, you know, all the other elemental contributions in the correct places. Okay? So I know, you know, we've done a lot of practice doing this, but definitely make sure that, you know, you get this down, because it's one of those things where it's a really small detail, but it makes a really big impact on the results. Okay? You know, and that kind of goes through for everything right here. Okay. Okay. So after we've assembled the global system, you know, the next step is that we need to apply our boundary conditions. Okay. And remember, we have two types of boundary conditions. So we have one type called Dirichlet boundary conditions and another type called Neumann. And then the way that we, or what they actually physically are in our structural system and how we actually put them into our global matrix are different. Okay? So let's go over that on the next page. Okay. And so first, let's go over Dirichlet boundary conditions. Okay. And so the formal definition for a Dirichlet boundary condition, you know, because, you know, we're going to use this terminology when we solve like heat transfer problems, is that Dirichlet boundary conditions are direct specifications of our solution variables. Okay. And so by solution variables, what I mean is the types of quantities that are in our solution vector. And so if you remember kind of the general form for our global system, it looks something like this. Okay. And so remember this big K right here, this is our global stiffness matrix. Okay. This F right here, this is our global forcing vector. Okay. And this U right here, this U is our solution vector. Okay. And so usually for a lot of these finite element problems, all the entries within the solution vector, you know, those represent the solutions to our problem at all the nodes in our system. Okay. And they're usually all of the same type, or they're all very, very similar types. And so for, you know, the direct stiffness method that we've been working with, you know, everything that's in the solution vector has units of displacement. Okay. And then, you know, when we're doing beams and frames, you know, this we also include rotations in here too. Okay. And so any type of boundary condition that says, you know, the displacement at this node has to be X, or the rotations at this node has to be, you know, Y or something like that, where we're directly specifying the values of what should be in this vector right here. Okay. So any type of boundary condition that places the requirement on, you know, the actual values of our solution, these are Dirichlet type boundary conditions. Okay. And so for basically all the cases that we've seen so far in our direct stiffness method, is that Dirichlet boundary conditions are referred to constraints. Okay. Because what do constraints do, right? So constraints are basically just like a restriction on how much something can deform, right? And so if you take like a beam and you kind of anchor it to the wall, what you're saying right there is that at the location where your beam is anchored to the wall, that part of the beam cannot move, right? So any node that's attached to a constraint, we're basically saying the displacement and the or the rotations, depending on what type of boundary condition it is, has to be 0 at that location. Okay, and so by requiring that the solution or the displacement has to be 0, these are kind of our displacement type boundary conditions. Okay? And for all the problems that we're going to do, you're going to see at least one of these, because otherwise, if you don't supply one of these, the problem's actually unsolvable. And so for any type of finite element problem, you know, there always has to be at least one Dirichlet boundary condition, because that kind of sets your the baseline for everything. Okay? If you think of a situation in real life, right? If you have kind of an object that's kind of floating in space, you can hold it in place if you have two equal and opposite forces, you know, but that's usually not the case. But that's usually doesn't happen as perfectly as that. So what's typically more common is that you attach that object to something solid. So you can say, you know, you have an object resting on the table, and that table could be like your Dirichlet boundary condition, because that prevents, you know, displacement. And then you apply a force on top of that. Okay? So most problems that you'll see, you know, will have at least for this direct stiffness method, there'll always be at least one Dirichlet boundary condition and one Neumann. But after the midterm, we're gonna relax this a bit. But no matter what type of problem that we're doing, you know, 99% of the time, you know, you're gonna have at least one Dirichlet boundary condition. And the only cases where you don't are very, very special cases that, you know, a lot of times are not usually that practical. Okay, so that's Dirichlet boundary condition. Oh, actually, let's talk first about the way that we're going to deal with this in our global system. Okay, and so Dirichlet boundary conditions. Remember, the way that we deal with them is that we use well, there's two methods now, but the method that I recommend the most is the row replacement method. Okay. And so what the row replacement method is that we first we identify the row in our global stiffness matrix that we need to apply the boundary condition on. Okay? And so usually that's by identifying, you know, which degree of freedom at this node are going to be constrained. Okay? And then once we know that row, then we basically replace that entire row with zeros. Okay. But we're not done yet. And so another thing that you have to do is that you have to place a 1 on the diagonal. Okay. And so basically what you'll see in your global system is something like this. And so say that, you know, we have a Dirichlet boundary condition on something like this, right? And so what we're going to do first is we're going to replace this entire row right here with zeros. Okay. I say that it goes on down here. Okay. 0 over here too. Okay. And then the diagonal entry, which is basically the entry on that row that has the same index as the column, we're going to replace that with 1. So that's going to be this guy. Okay. Right. And so we talked about this briefly at the end of the frame equation notes. But this value that we have over here, this is actually your Dirichlet value. Because you know, if you actually perform the matrix multiplication of this row right here and this column, okay, basically just the row where you have the Dirichlet boundary condition and the solution vector, if you actually perform the matrix multiplication, right, then what you get is on the left-hand side you get u, in this case u1x, or whatever variable that you have over there, okay, and this has to be equal to whatever is given in this entry right here on the right-hand side. Okay, and so since we have 0 right there, that's going to be ux is equal to 0. Okay? right? So this is kind of the mathematical reason of why we do the row replacement method, because the row replacement, basically what we're saying is we're going to replace, basically remember every row in this matrix is basically a linear equation, right? And then we stack them on top of each other, and then we have a system of linear equations. And so with the row replacement method, what we're saying is we're going to replace that first equation with this very simple one right here, where we directly specify the value. That's why we have this form, because all the zeros here are going to multiply with all the other degrees of freedom, and then the 1 is going to multiply by whatever one that we're going to specify here. Okay? And then on the right here is our Dirichlet value of what we're going to set that displacement to be. Okay? And so for so for everything in our structural problems, we're going to use a Dirichlet value of 0, because the only Dirichlet condition that we're dealing with is a fixed condition, which sets the displacement equal to 0. But for other problems, that we'll see later, like heat transfer or fluid mechanics, we'll set the actual value for the Dirichlet value to be something else from that. Okay. And so that's the row replacement method. We talked briefly at the end of the frame equation notes about the row deletion method. So just kind of deleting these rows and columns. So if you want to do that for these kinds of problems, you're definitely free to do so. Again, just make sure you kind of show me all your work in doing that. Okay. So that's Dirichlet boundary conditions. Another name you might hear about those types of boundary conditions in practice is called essential boundary conditions. Okay, but we'll stick with the Dirichlet naming convention, because that's a little bit more formal, a little bit more applies to other things as well, right? And so the other type of boundary condition that we're going to look at are Neumann boundary conditions. And so Neumann boundary conditions, you can kind of think of them as kind of external loads or external effects that are being applied onto your system. Okay. And what's unique about Neumann boundary conditions compared to Dirichlet is that these don't involve the solution variables directly. Okay. And so remember, for Dirichlet boundary conditions, we're thinking of things like specifying the displacement at a certain point. But for Neumann boundary conditions, we're thinking of things like forces and for moments, right? Things that we know are going to have an indirect effect, or not an indirect, but they are going to modify the displacements in our system, but it doesn't directly specify these exactly. And so for direct stiffness method, these will be things like forces and moments. And so some other examples of Neumann boundary conditions that you'll see in other types of finite element simulations will be things like heat flux, will be things like pressure or stress. So heat flux would be like for heat transfer, and pressure and stress would be for fluid mechanics. Okay. Okay. And so the nice thing about Neumann boundary conditions is that they're relatively a lot easier to specify. So we only basically just do it in one step. Okay? And that one step is basically we're just going to add their value onto the forcing vector. And so again, the most important thing for this is that we add these values onto the appropriate row. Okay, and that's going to be kind of the most important thing for this. Okay, but besides that, the Neumann boundary conditions are pretty simple. And they're usually pretty clear in our diagrams too, because there'll be either some kind of force or moment that you can kind of directly see. Okay. So that's the summary on the boundary conditions. And so once you've applied the boundary conditions onto our global system, at that point you can go ahead and solve. Okay. And solving the linear system of equations, most of the time you're going to do this in MATLAB, just because otherwise it just becomes really unwieldy to do by hand. And so, this is, for most cases, this is kind of the most time-consuming part of the computation. And so it really helps to kind of have the computer do this kind of the heavy lifting for us. Okay. And that's basically it for the stiffness method. So remember, the stiffness method, the most important thing I want you to get from those notes is more just this process of, how do we actually get to this point, or how do we actually solve these kind of finite element problems with the direct stiffness. Okay. And so, before we actually move on to the frame equations, I do want to highlight kind of the part here that's kind of the most, we're going to use this process of solving finite element problems for every type of equation that we have. But, the most important thing is this guy, okay? The element stiffness matrices, right? And so I know we've commented before that every element has a different type of element stiffness matrix, okay? And for all the different types of finite elements that you can do, all the different types of equations and all the different types of meshes and stuff like that, the thing that really defines a type of finite element method is its element stiffness matrix, right? And so and that's kind of how the direct stiffness method gets its name, because the direct stiffness method basically works directly off of the governing equations for that type of element. Okay? And so for a spring, we saw that the element stiffness matrix simply just got by getting the force and displacement relationship between them, and then basically just making one equation the negative of the other one. But for every type of truss, and for beams, and for frames, every type of element has their own equation that governs their behavior, and you can think of the element stiffness matrix as kind of the matrix kind of manifestation of that. Okay? And what you'll see later on is that this element stiffness is not only a combination of just the equation, but also the type of element that we put on there, the shape of the element, how many nodes are in the element, and stuff like that. Okay? And so once we get to 2D problems within the kind of I would say it's more general finite elements, you'll see that kind of thing where it's going to depend on both the equation and the type of. But for now, everything that we've been doing up to this point with direct stiffness, you can kind of think of them as one-dimensional elements. I know we've been doing 2D problems, but our elements themselves are kind of just like sticks, right? So they're not actual, they don't actually have a thickness or anything like that. They have a cross-sectional area, but that's just a parameter that we specify. But then later on, once you get to 2D, especially for your project, that shape is going to be something that's going to be really okay. So that's the kind of the summary of the direct stiffness method. So it's just the a summary of all the process that we've gone through. And so now let's actually apply it to some problems that you might see. Right? And so the first application area, which is the one that was most heavily voted, was frame equations. And so before I start this, I do want to note that what we went over last Wednesday with the MATLAB implementation, that's not going to be on the midterm. So I'm not going to ask you to write MATLAB code on the midterm. I might ask you to solve a linear system of equations just like you did in the homework, but to actually write and implement like a working MATLAB code, I'm not going to expect that on the exam. So you don't have to worry about that. And so all I'm worried about in this type in these for this midterm is, can you set up the finite element problem by hand correctly Can you write down all the element stiffness matrices? Can you assemble the global system? And can you apply the boundary conditions? So that's going to be kind of the most important thing, and that's what I wanted to kind of drill into your brains right now. Okay. And so frame equations, this was kind of the last direct stiffness element type that we went over in this first part of the class. Okay? And it's unique in that you can kind of think of it as kind of the fusion of all the other of all the elements that we went over so far, except for springs. But springs are kind of their own thing. Okay? And so before getting to frames, the primary things that we covered was like the truss element. Okay. Also sometimes called a bar. Okay. And what was unique about the truss and the bar was that it could only displace axially. Okay. And so by axial displacement, what I mean by that is, they can only compress, they can only be given in compression or tension. Okay. And so if we draw kind of a typical truss element right here, and so we have this kind of rectangular bar. Okay. It can basically only displace in this way. So this would be tension. Okay. And then the other way that it can displace is this way. So we have our bar, and then we have the arrows going like that, and this is compression. Okay. So that was the truss. That was the truss element. Okay. And so the other one that we went over was beams. Okay. And what was unique about beams is that they could displace in both the transverse direction and also they could rotate, okay, or have local rotations. Okay. And so if we draw kind of a beam element like this, let me box these guys. So this would be like transverse displacements and local rotations. Okay. And so a transverse displacement is a displacement that's kind of perpendicular to kind of the long axis of the element. Okay. And so a transverse displacement might look something like this. So you might have displacement up or down. Okay. And then associated with that, we also have our local rotations, which means that the ends of the beam can actually rotate, something like this. Okay? And so you might have a change in orientation where the beam might dip a certain way. And the way that we can characterize that is with the rotations. Okay? And so because the truss and the beams are only able to support just these kind of basic type of deformations, it kind of limited them in solving certain kinds of problems. So if we wanted to use truss elements on a problem, we had to make sure it would be a situation where the primary modes of deformation would be just compression and tension or axial, right? And the same thing for beams. So if we wanted to use a beam in a certain problem, we had to make sure that the only way that the primary ways that it actually deforms was in the transverse direction or with local rotations. Okay, but a lot of realistic situations aren't nice like this. So a lot of realistic situations, they're going to have all these kinds of things. Right? And so the answer to that is the frame. Okay, and so the frame element can support all these types of deformations. Okay? And the nice thing about frames is that, we didn't, for the trusses and for the beams, we went through kind of a somewhat lengthy process of saying, these are the equations that form the element stiffness matrix. And so we kind of went through a lot of, the structural mechanics, and this is the equations, and this is how we get a linear equation out of this. For the frame, we actually don't have to do that because all that work's kind of done for us. And so for the frame element, we're basically just going to be borrowing the element stiffness matrix for this truss and the element stiffness matrix for the beam, and then basically just clubbing them together. Okay. And so because of this, the element stiffness matrix, or let's talk about the degrees of freedom for a frame element first. Okay. And so because the frame element can support all these different types of deformation, the degrees of freedom for the frame element are going to be, all three types of deformation at each node in the element. Okay. Okay. And so if we draw our beam our frame element right here, okay, and we call this node 1 on the left-hand side, and we'll call this node 2. Okay. And so the frame element is going to support all three of these guys. Okay. And so at node number 1 right here, we're going to have a U1x, which is a displacement in the x direction. Okay. We're going to have a U1y, which is the displacement in the y direction. And we're also going to have a theta 1, which is the local rotation of the frame at that location. Okay. And then we're going to have all the same things at node number 2. Okay. And so because we have 6 degrees of freedom per element, okay, what this tells us is that the element stiffness matrix will be a 6 by 6 system. Okay. And so it's pretty big. So it's we're going to have 36 unique entries that we need to specify. Okay. Okay. And so, you can definitely find the expressions for all of these in the notes. You can actually find kind of a nice expression for in the lecture slides, in the slides for the implementation. Okay. And so I'm going to do something I didn't do before. So I'm going to attempt to write the whole thing. Okay. I think we have a bit more time here, or maybe not. I want to make sure I do an example for the frame. So I think we'll hold off on writing the whole thing. But there's tons of places you can view the element stiffness matrix for a frame element, and it's you can find them in the lecture notes. You can find them online. Just make sure that you kind of have that handy, because it's big and it's kind of easy to kind of make some computation mistakes. Oh, and I've also posted that MATLAB script to help you compute the element stiffness matrix for a frame as well. So definitely make use of that as well. Because it's a lot of manual calculations, and it's very, very easy. Like when you're doing 36 manual calculations, it's very easy to kind of miss a number or miss a parenthesis like that. So I don't want you guys wasting time on the midterm doing all those manual calculations, because in reality most of the time those are done by the computer anyway. So definitely focus your time on just doing the problems. Okay. Okay. And so the example that I wanted to do, let me kind of rework one of the examples that we did in the class, but I'll change it up a little bit just to kind of make this review a little bit fresh. Okay. And so this is going to be just a frame equation, but it's going to be 2 elements. Okay. And this example is going to have a distributed loading as well, just so you can kind of get a taste of that. Okay, and so let's say that we have our system like this, right? So we have two elements A and B. This is node number 1. We'll call this node number 2. We'll call this node number 3. Okay, right? And then let's write out some of the properties. And so let's say that this angle right here is 45 degrees. Okay. And so the length right here will be 30 feet. And so the length here will be 40 feet. Okay. And so let's write out some of the properties. So we have Young's modulus is equal to 30 E6 psi. We have A is equal to 100 inches squared. Okay. And then we have I equal to 1,000 inches to the 4th. Okay. And so those are all kind of the properties that we need. Okay. And now we need to put our loading here, because you can see we have two fixed conditions, and so we need to have some kind of loading in order to get something interesting. And so in the notes, I did kind of vertical load that was going up going down like this. Okay. But let's not do that for this one, because we've kind of already done that in the class. And so let's do an example where we have a positive load, so we're kind of lifting it up, but it's going to be a ramp instead of a constant. Okay? And so let's say that our load looks like this, so it's going to be a ramp. Okay? And so we're going to be pulling it up, and then instead of a constant, or it's instead of pushing down, we're pulling it up, right? And then our function will be given by the following. So it looks like in the notes we have 1,000 pounds per feet, and so let's have 500. Now let's take it down a little bit. So let's say that we have 100 times x, and so x here will be the distance along the element. Okay, pound per feet. And so instead of being a constant here, we have this this variable x, which is going to modify our computation of the force. Okay, and so this is a problem. And so let's kind of run through our process for the direct stiffness method that we talked about before. Okay, and so first thing to do, let's just kind of analyze this geometry and kind of just note a lot of the properties that we have here. Okay? And so we've written a lot of them down, but just some other things that we can take note is that we have two elements. We have A and B. We have 3 nodes, right? Boundary condition wise, we have nodes 1 and node 3 are going to be fixed, right? And so what that tells us is that we're going to have Dirichlet boundary conditions on on all of those guys, okay? And so our Dirichlet boundary conditions, all the degrees of freedom associated with nodes 1 and 3 are going to be 0. So we have U1x is equal to U1y is equal to theta 1 is equal to U3x is equal to U3y is equal to theta 3. All these are going to be equal to 0. Okay, and so those are Dirichlet boundary conditions. So for these kinds of problems, sometimes it pays to kind of write them down ahead of time. Okay? And then for our Neumann boundary conditions, those are going to come from our distributed loading. Okay? And so for these kinds of problems where you have distributed loading, before you actually launch into computing the element stiffness matrix and assembling at the boundary conditions, you have to actually compute the nodal loads. Okay? And so first thing we're going to do is we're going to convert this distributed loading into nodal loading. And remember, the way that we do this is we're going to use the principle of equivalent work. Okay. And so we're going to run through kind of that lengthy kind of integral process in order to do that. Okay. Okay. And so let's go ahead and start. And so our principle of equivalent work, remember, we're going to take an integral from 0 to L of w of x, which is our load function, times uy of x, okay, dx. And then this is going to be equal to the corresponding nodal load. So then there's going to be f1y, u1y plus m1 theta 1 plus f2y, write that down, f1y, f2y, u2y plus m2 theta 2. Okay. And so let's go ahead and plug in our expression for u y of x and then multiply it by w of x. Okay. So let me use a kind of a thinner pencil here. Okay. And so by plugging in for this side of the equation right here, we're going to get integral from 0 to L of w of x, which is a positive 1, that, or what was it, 100x? Yep, 100x. Okay. Multiplied by 2 over L cubed u1y minus u2y plus 1 over L squared theta 1 plus theta 2. Okay. And so all of this is multiplied by x cubed, okay, plus minus 3 over L squared times u1y minus u2y, okay, minus 1 over L 2 theta 1 plus theta 2, okay, and all this is multiplied by x squared, okay, plus theta 1x plus u1y, okay, all this multiplied by dx. And so the way we're going to solve this is we're going to, in the past, we've been able to just simply integrate this, but because we have that extra x out in front, we need to distribute this x through and then perform the integral. Okay. And so let's go ahead and do that on the next page. Okay. Okay. And so by distributing x through, we have 100. Okay. Multiplied by integral of 0 to x, or 0 to L, sorry. And then multiplied by 2 over L cubed times u1y minus u2y, okay, plus 1 over L squared, theta 1 plus theta 2, and then x to the 4th, because we're going to multiply everything by x, okay, plus minus 3 over L squared, u1y minus u2y minus 1 over L times 2 theta 1 plus theta 2 x cubed plus theta 1 x squared plus u1y x, okay, dx. All right, so then now let's go ahead and perform this integral. And so now we're going to have 100. Draw a line here. 100 multiplied by 2 over L cubed times U1y minus U2y, okay, plus 1 over L squared, theta 1 plus theta 2, okay, and then it's going to be x to the 5th over 5, okay, plus, let's see, minus 3 over L squared, U1y minus U2y, okay, minus 1 over L, 2 theta 1 plus theta 2, x to the 4th over 4, okay, plus theta 1 x cubed over 3 plus u1 x squared over 2, and all this can be evaluated from 0 to L, okay? And so now we're going to plug in L in for everything and then perform the multiplications from there, okay? Okay, so you need to cool off my hand a little bit. Okay, so let's go ahead and do that. So we have 100 multiplied by a 2 over L cubed u1y minus u2y, okay, plus 1 over L squared, theta 1 plus theta 2, okay, and then we plug in L for this, we get L to the 5th over 5, okay, plus minus 3 over L squared, u1y, minus u2y, minus 1 over L times 2 theta 1 plus theta 2, okay, and all this is multiplied by L to the 4th all over 4, okay, and then plus theta 1 L cubed over 3 plus u1y L squared all over 2, okay? Okay, and so we had the 0 term, but then that just canceled out, okay? And so let's, and then now at this point, you're gonna plug in L is equal to 40. Okay, L is equal to 40 feet, and then you're gonna distribute to 100, and then from then you're gonna get expressions for F1y, M1, F2y, and M2. Okay, and remember these are going to be the equivalent nodal nodes for this system right here. Okay, and so once you do that, we can go ahead and plug them back into our system. Okay, so let me increase the width here. Okay, and so by including all those, we get a nodal node just like this. Okay, and so because we have a lopsided one, our nodal node on node 3 is going to be bigger because of our ramp, right? Okay, and then we're also going to have our moments. Okay? This is going to be M2, M3, okay? And then from here, we can basically just follow our same kind of direct stiffness process, okay? Okay. And so I'm going to let you kind of do that part on your own because I am running a little bit short on time. But I do want to write at least the element stiffness matrices because we spent all this time before in this review session talking about element stiffness matrices, assembly, and boundary conditions. I want to make sure I touch on that a little bit. Okay. And so let's go ahead and assemble. And so the way that we usually do these for these kind of elements is that we start by at least listing all the properties for that element, and then we compute some key quantities. Okay. And so for element A, which is this guy, okay. And so for element A, we know that the angle for this is going to be 45 degrees. Okay. And so with 45-degree angle, we know that cosine of this angle, which we shorten by c, is going to be √2/2. And sine of this angle is going to be also √2/2. Okay. And then let's compute some of these other quantities. So we have 12 I/L squared. And this is equal to 0.185 inches squared. Okay. Then we have 6I/L, and this is equal to 23.57 inches cubed. Okay. And then we have E/L, which is number of factor in front. This could be 1.179 E5 pounds per inch. Okay. And so if we plug all these into our expression, we get the following. Okay. So let me see. I'm going to write sideways on this just so you guys can see, but let me see if the iPad will rotate. Okay, iPad won't rotate. That's okay. Okay. And so just so I can fit it all, I'm going to write it sideways just like this. Okay. And so we have Ka is equal to, and we'll see how many I can fit in here. Right. And so we have 4.42 E6. Might help to actually use the thinner pencil here. 7.07 E6. Okay. Minus 4.28 E6 minus 4.42 E6 okay. Minus 7.07 E6 and then minus 4.53 E6 E4, sorry. Okay. And so that's the first column. So second column, we have 7.07 E6, 1.15 E7, 2.64 E6, minus 7.07 E6, okay, minus 1.15 E7, and 2.64 E6. Okay. Right. And then maybe I'll just do one more column. Minus 4.28 E6, 2.64 E6, okay. 6.34 E8, 4.28 E6, minus 4.28 E6, 3.17 E8. Okay. All right. So I know it's sideways, but you can imagine that this goes on just like that. Okay. Okay. And so once you have these element stiffness matrix, this is for element A. You would do the same thing for element B and get their element stiffness matrix. You would apply the boundary conditions that we talked about at the beginning. You would assemble them together, and then solve, and then you would get the solution. And so this solution, is going to be different than the one in the lecture notes, just because we have different loading. But just as a good practice, might be good to run through this. Okay? And so this example here, I know that there's there's like a million different combinations of different elements that you can try for these, you know, but like just when you're starting out, or, you know, if you're looking to do more practice problems with these, because, you know, the more you practice these, the more you kind of get used to it. Just look at some of the other homework problems or other examples that we did and change things around a little bit. Maybe change the properties around a little bit, change the loading, change the Dirichlet boundary conditions, and then, you know, redo the problems like that. You'd be surprised at seeing, you know, how different things can be when you change something up like the boundary conditions or the properties. So it really can make for like an all new problem. So, you know, when you're studying for the exam, you know, I would definitely recommend doing that. But besides that, you know, there's, you know, everything in this unit is kind of just follows the same process. And so, you know, it kind of feels like we're just kind of beating this thing over the head by the same process. But, you know, this is kind of the essentials of what the finite element process is. Okay? And so even once we do this stuff after the midterm, you know, we're going to still do a very similar process. It's just the thing that's going to change the most is, you know, how we get our element stiffness matrix. And how we get that is going to become a big subject of the part afterwards. But, you know, I wanted to start this class with this just to give you kind of an overview of, you know, what the finite element process is, and then from there we can kind of build on this and to do more complex problems. Okay? And so with that, you know, that's all that I can do with this review session. Mostly just because I have to give a midterm in another class and very soon. But, you know. Hopefully, you know, this midterm review is helpful. You know, as always, you know, if you have any questions about anything, definitely let me know. I'm always happy to answer any questions. So best of luck with your studying, and I'll see everyone on Wednesday for the midterm. But we also have lecture on Monday, so don't skip that.